Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process. Mother Earth is a biological living trust. Let us not destroy her in the name of development, armed with the power of modern soulless science and technology. It is a very important thought that we must ponder about it because of climate change and then other problems what we are facing. So, let us recall what we learnt in the last lecture. In the last lecture, we basically discuss about composite propellants and its constituents, and then later on we also find out various kinds of the propellants, fuel and oxidizer that can be utilized for developing composite propellants. Then we have also looked at the modified double base composite propellant, and later on we also looked at characteristics of a certain composite propellant, and we found that one can look at theoretical analysis to design a composite propellant according to certain guidelines for certain application. And then we also learnt how to manufacture the composite propellant. If you recall, we looked at two methods, one is casting, other is solventless extrusion process, which is both of them are similar to the manufacturing process of double base propellant, but there is a lot of differences you could have noticed. Today we will be discussing about liquid propellant. So, liquid propellant can be classified on various ways. One way we can classify as basically based on the ignition, that is the hypergolic propellant and non-hypergolic propellant. Hypergolic propellant means that the propellant can be ignited without any aid of external energy or the ignition energy, and therefore, one has to be little careful about hypergolic propellant, particularly while handling and storing it, and because it can ignite itself. Whereas, non-hypergolic propellant is one in which one has to provide requisite ignition energy, so that initiation of combustion of the propellant can be really taken place. And hypergolic propellant is again divided into two categories. One is monopropellant, mono means single, right, and bipropellant means the two propellants will be used. And of course, the single propellant there are several kinds. Some of the examples are hydrogen peroxide, hydrazine, and keep in mind that this single propellant can be decomposed into their products, particularly when it is heated or it will come in contact with the catalysts. For example, like if you look at the hydrogen peroxide can be decomposed into hydrogen and oxygen whenever it will come in contact with catalyst, and can give rise to 1588.5 kilojoule of kg of heat, and as a result this heat can be transferred to the propellants product, and so that this high temperature high pressure gas can be expanded in a nozzle to produce the thrust, and thus with this very simple monopropellant one can achieve ISP of 147 seconds. Of course, this is a very simple system, nothing really is to be required except you are having a combustion chamber and nozzle, and that is why it is being used, but its application is very limited because of fact that it is having specific impulse, very low specific impulse. Therefore, it is being used particularly in a space applications wherever one has to use for a short time, and also for let us say orbital reorientation of the satellites, and such that it can be utilized very easily. And bipropellant is one in which both the fuel and oxidizer can be used, and this is of course the under the comes under the hypergolic propellant, and some examples are UDMH, that is unsymmetrical dimethyl hydrogen as a fuel, and RFNA as a oxidizer. RFNA means rate fuming nitric acid, and as the name suggests that some fuming, red color fuming will be coming out of it, because it will be having water and also nitrogen tetroxide to some extent, and therefore, of course, it is having little higher performance as compared to the white fuming nitric acid or the simple nitric acid. And these both are hypergolic in nature, and it is being used in India very much, and it can be stored easily. Of course, it is little toxic in nature, and one has to be careful about using it. And nitrogen tetroxide and nitric acid is another example of hypergolic bipropellant, which is also being used, and this can give a moderate range of ISP, or rather we call it as a lower range of ISP. And the non-hypergolic propellant can again broadly divide two categories, one is monopropellant and other is bipropellant. And the monopropellant non-hypergolic propellant can be again further divided into simple and composite propellant, and simple propellant is one which will be containing both the fuel and oxidizer in the same molecule. If you recall, in the double base solid propellant also contains the fuel and oxidizer in the same molecule in the molecule. So, therefore, it is similar to that, but it is in liquid state, and one example is methyl nitrate. Whenever it will be ignited, that will be decomposed, and you can really undergo the chemical reaction, exothermic chemical reaction, and producing certain amount of heat. And it is a very simple one, non-hypergolic monopropellant, which is used again similar to your hypergolic monopropellants. And there is also a composite. Composite means a mixture of oxidizer and fuel is being used as a propellant. Example is nitric acid and amyl acetate can be mixed together, and it can be in certain proportion. It can be used as a monopropellant, but for this one has to provide certain amount of ignition energy to initiate the combustion. And the non-hypergolic bipropellant is being used very much, but it is quite safe, and also it will be easy to control a lot of things. It can give a little higher ISP, and the example is the liquid oxygen, liquid hydrogen, which gives the highest specific impulse. So, beside this, like you can use also liquid oxygen and kerosene, and you can use also other propellants as a fuel and oxidizer is being used profusely. So, we can now classify the liquid propellant based on energy. So, that can be divided into three categories. One is the low energy propellant, medium energy propellant, and high energy propellant. Generally, energy means how much of energy will be released per unit mass of the propellant, but however, it will be interesting to look at instead of energy in terms of specific impulse. So, low energy liquid propellant will be basically one whose ISP ranges from 140 to 300 second. and medium one is greater than the 300 second, but it will be less than the 400 second. That means, the medium energy liquid propellant will be can produce something around between the specific impulse in the range of 300 to 400 second, and high energy liquid propellant must be having ISP greater than 400 second. So, let us look at some of the examples of low energy liquid propellant. If you look at hydrogen peroxide, this is your hydrogen peroxide. Hydrogen and methyl nitrate are basically monopropellants, which can produce a low energy ISP in the range of 140 to 30 second. If you remember that hydrogen peroxide and hydrogen are basically hypergolic in nature, whereas methyl nitrate is non-hypergolic. This methyl nitrate is non-hypergolic propellant. And beside this, there are several other propellants, bipropellant, particularly aniline, RFNA, that is red fuming nitric acid, xylidine and RFNA, UDMH and N2O4, MMH, that is monomethyl hydrogen and nitrogen tetroxide, and hydrogen and nitrogen tetroxide, RP means rocket propellant, and liquid oxygen. And keep in mind, this is basically a propellant which is known as semi cryogenic propellant, because liquid oxygen has to be cooled such that it will remain in the liquid state at a ambient temperature. And alcohol and liquid oxygen, even this is also is a semi cryogenic. So, other examples, if you look at the example of medium energy liquid propellant is UDMH and LO2. This again, when you use the liquid oxygen, is a semi cryogenic kind of things. And high energy propellant is liquid oxygen and liquid fluorine. Keep in mind that this can give a highest specific impulse order of something maybe 465 kind of seconds, and but it is not being used very much, because it is difficult to handle the liquid fluorine, and it can be noted that liquid fluorine will act as a oxidizer in this case, where the liquid oxygen will be acting as a fuel, because the liquid fluorine will have higher electronegativity as compared to the liquid oxygen. This is a very interesting case. You should keep in mind that where the liquid oxygen is acting as a fuel, and liquid hydrogen and liquid oxygen, this is a widely used propellants, and this is all are basically cryogenic propellant. This is a cryogenic, and the liquid hydrogen, liquid oxygen can provide specific impulse around something 450 second. And we can also classify liquid propellant based on the storability. It is a very important thing that we need to store the propellant for a longer period without undergoing any chemical or thermal changes. And we know that the rocket engines, liquid propellant rocket engines having lot of application. It can be applied for missile application, it can be applied for space launching vehicles, it can be used for the space satellites, and putting the satellite, or also taking care of attitude control of the satellite, and several others. So, therefore, this is a very important one to classify the propellant. This propellant, liquid propellant, can be divided into two categories based on the storability. One is the earth storable propellants, and other is the space storable, because earth storable is a one which will be remaining as a liquid, should not undergo the changes during its storage, and all these propellants whatever we have discussed here, these are the propellants which can be stored very easily on the earth. Therefore, this we can say earth storable, because this propellant can remain in the liquid phase at ambient temperature and pressure. So, therefore, it can be easily stored on the earth, whereas the semi cryogenic propellant, one has to be provide the insulations and properly and having a vent, so that the if some of the propellant will vaporize, it can be escaped without undergoing any explosion or any other mishap. So, therefore, it is very important to look at it, whereas the space storable should have a having low boiling point and high freezing point, and this is a very important aspect because of fact that the propellant in the space has to be stored for a longer period of time and at a very low temperature. And beside this, for the missile applications, if you look at, we cannot really fill the propellant tank with the liquid propellant immediately, because you will have to store it such that it can be used at any instant during any emergency of external aggression. So, therefore, it is important to have this look at the storability of the propellant, and if you look at the space storability is also very important. For example, nitrogen tetroxide is having freezing point around 9 degrees Celsius, which is quite low, but it is not suitable for space storage due to its higher freezing points. Now, question arises, what will be the solution? People have used this is the mixed oxide of nitrogen, that means nitrogen tetroxide will be mixed with the nitric oxide, and if you look at this MON3, which is a mixed oxides of 3, which indicates that 3% of nitric oxide is added to 97% of nitrogen tetroxide. As a result, one can get freezing point increase from minus 9 degrees Celsius from the virgin 9 N2O4 to something minus 15 degrees Celsius. And when this NO percentage increase to 25%, then you will get the freezing point of minus 55 degrees Celsius, which is quite lower as compared to the virgin nitrogen tetroxide. Therefore, one can really manage with this, and keep in mind that this is a very important thing one has to classify the liquid propellant. So, hypergolic propellant, if you look at in the presence of catalyst platinum, silver, ferric oxide, magnesium oxide, there are several catalysts one can use, and one can look at it can decompose hydrogen peroxide into hydrogen and oxygen, and will be releasing certain amount of heat energy. And hydrogen, when it comes in contact with iridium catalyst, it can decompose into this 1 moles of hydrogen can be decomposed 2 moles of ammonia and 1 moles of hydrogen, and ammonia will be further decomposed into hydrogen and nitrogen. So, of course, various kinds of catalyst can be used, and then one can get a temperature of 1700 Kelvin and specific impulse of 245 seconds when it is operated at chamber pressure of 7 megapascal. And of course, keep in mind that these are all hypergolic propellant and then monopropellants, and it is generally used for small rockets for altitude control and gas generator for turbo pump and turbines kind of things in a rocket engine. So, that it is easy to handle, it is a simpler one. And beside this, unsymmetrical dimetal hydrogen and RFNA, that is red fuming nitric acid, is being used in India and also other places due to its higher performance, and also it is easily available. And let us look at some of the common liquid oxidizer and common liquid fuels. And as I told, liquid oxygen and liquid hydrogens are being used profusely nowadays as a cryogenic engine, and of course, the hydrogen peroxide is being used. As I told earlier, red fuming nitric acid is basically a mixture of nitric acid, nitrogen tetroxide and certain percentage of water, and it is used for missile with aniline and gelyline fuel and others also UDMH. And whereas the white fuming nitric acid is a liquid oxidizer, which is basically little less toxic in nature, as it does not contain nitrogen tetroxide or very minimal, maybe negligible percentage. And beside this, the fuel, if you look at saturated, unsaturated hydrocarbons are being used, and like kerosene, this rocket fuel, which is basically modified kerosene, alcohols, amines are being used, and tetranitromethane TNM is not being very much used, but however, it is a potential oxidizer. And beside this, the boron, which is the hydride of the boron and which is having a good qualities, but it is not really being used and as a fuel. And nitrogen tetroxide, which is profusely being used, it has been used in the Titan missile as a nitrogen tetroxide with a mixture of UDMH and hydrogen. And the space shuttle also it is being used as a nitrogen tetroxide as oxidizer and MMH as a fuel in Bicas engine for PSLV and GSLV. And of course, the liquid fluorine is a very exotic fuel and which can provide a higher ISP along with the liquid oxygen, but it has not been used very much due to its corrosive in nature. And let us look at the optimum performance of certain bipropellants, and this is AE by A star ratio. This area ratio of the nozzle is 40, chamber pressure is 6.89 megapascal and back pressure is 0 megapascal, is almost space. So, you can look at that liquid oxygen, liquid hydrogen at the oxidizer fuel ratio, that is the stoichiometric, will give you 3251 Kelvin, and this is basically theoretical values, and average density is very low, 0.32, hydrogen being a lighter molecule, right, and you can get a characteristics velocity of 2386, ISP will be getting 455 second. And whenever the liquid methane is used in place of liquid hydrogen, of course, the density has increased and the characteristic velocity has been decreased, and so also the specific impulse. And that is true with the RP fuel. And but whereas if you look at this is liquid fluorine and liquid hydrogen, when you use you will get a very higher specific impulse, that is 479, and of course, that is not being used very much, but maybe in future when good material will develop, then we can use that. Nitrogen tetroxide, and as I told earlier, the mixture of nitrogen hydrogen and UDMH 50% has been used in lunar module, which can give you something 342 ISP. And also nitrogen tetroxide MMH can give you also 342, and keep in mind that this has been used in as a lunar module Apollo 11, that is a combination is known as Aerogyne. Even nitrogen tetroxide with MMM as UDMH is used in Apollo command and service module. And of course, the liquid oxygen, liquid hydrogen used for space shuttle. These are all being used very much nowadays as a cryogenic engine. With this, we will stop over. In the next lecture, we will be discussing about the solid propellant rocket engine. Thank you very much.